All right, so I see that there's actually a fair number of X-ray people on this on the participants list. So if you're one of them, prepare to be bored. Um, I am going to, or feel free to nitpick as well. That's always welcome. Um, but yeah, today I wanted to tell you a little bit about XRISM, which is, as Jess said, the X-ray Imaging and Spectroscopy mission. It is a JAXA-NASA partnership with contributions from ESA and also Canada. So we've already heard for the past 7 weeks, why hot gas is an important component of the CGM, why it's important that we have X-rays in order to study it. And it's kind of embarrassing that we're still in this phase where we really have not answered the big questions. These could be the big questions of life, but especially for the CGM, we'd like to know how much hot gas there is, where it came from, and what's going to happen to it. And XRISM is certainly not the instrument that is going to answer all of these questions, but it will help to answer these questions. And it is the next capability that we will have to do so. And if I had to summarize what XRISM will do for like L-star galaxies, excuse me, it would probably be, it won't do very much for the extended CGM. It's like beyond maybe 25 or 50 kiloparsecs, but it will do some very interesting work closer to the disk. So what is XRISM? Well, it is two telescopes with basically should have identical mirrors. In practice, they'll probably be slightly different due to fabrication. But there's two telescopes and two instruments. So the primary one is called Resolve. It is the microcalorimeter. That's what I'll be spending pretty much all of the rest of the time talking about. But there is also a CCD detector that is co-aligned and will be simultaneously observing. So Resolve is a quantum microcalorimeter. So this is an idea that has been around in the infrared and implemented, in fact, for a long time. But in the X-rays, it's sort of been the holy grail for a long time to produce one of these things and fly it and have it last more than, I don't know, a few weeks. The basic idea can be seen over here on the right. I can't see my own cursor, so I'm not going to bother with that. But if you see this block where it says heat capacity, so there's a detector pad, and a photon comes in and is absorbed in this detector pad, and that heats it up. And when that happens, we can measure the temperature very sensitively, and that temperature rise is what is proportional to the energy of the incoming photon, and that's how we measure the energy of the photon. So you can see in that graph just to the left of that, with this pulse, essentially we measure the pulse heights of incoming photons, and that's how we achieve a high resolution in a non-dispersive spectrograph. This requires things to be extremely cold because individual photons do not carry much energy. So there's a 4 or 5 stage cooler that cools down to about 50 millikelvin, and that's the operating temperature. Interestingly, we can use both mechanical cryocoolers as well as cryogen in order to cool it down. So even though the cryogen has a limited lifetime, XRISM can in principle keep operating for long after the cryogen has run out. In terms of what the capabilities of this thing are, the requirements are listed in the center. I would ask you to focus on the Hitomi values because so far we are, in instrument testing, we are basically replicating all of the performance benchmarks that Hitomi hit. So the energy resolution is going to be about 5 eV. The energy scale accuracy is certainly going to be better than 2 eV. The field of view is about 3 arc minutes, so not especially large. And the angular resolution is a little over 1 arc minute, which means that the resolution is not like Chandra. This is a much coarser imager. And then the cryogen mode lifetime is between 3 to 4 years. But as I said, beyond that, you'll be able to continue using it. It's just going to operate with slightly lower efficiency. The other instrument is called Extend. It's the CCD imager. It's 4 chips with a 38 arc minute field of view. So you can see from this inset, which represents the 35 active pixels of the Resolve detector, that the field of view of Resolve is a really small fraction of the field of Extend. So the idea is that Extend sort of tells you what you're looking at and how much light is being scattered into your field of view for resolve, etc. And there's other science you can do with it, but it's not a new capability, so we're going to focus on the microcalorimeter. So I thought that for the sake of people who are not as familiar with X-ray astronomy, it would be worth just briefly reviewing the different types of common X-ray spectrographs. I know there are other types out there, but these are probably the types you're going to be hearing the most about. So there are CCDs, or similar detectors, there's gratings, and then there's microcalorimeters. And in the X-ray astronomy world, the incoming event rate, the incoming photon rate for pretty much any source is low enough that you can detect individual photons. And so for CCDs, what you can do is a photon will hit the CCD, it will liberate electrons from the semiconductor, and then that will create a charge cloud or a current cloud. And that is going to, the size of that is going to correspond to a pulse, or a voltage spike, and then you can measure the energy from the size of that. Now, that allows you to have imaging spectroscopy like we have on Chandra XMM, but it is relatively low resolution. So most of the data that you see from X-ray astronomy is in fact this type of imaging spectroscopy. Chandra and XMM both have gratings. They also can detect individual photons and disperse individual photons. They have lower throughput than the CCDs. And in this case, you get higher resolution because, of course, as you all know, you disperse the light and you're able to achieve higher resolution. And as you also know, the gratings have a constant wavelength resolution, which means that you have higher resolution for lower energies. The microcalorimeters are kind of like very complementary to the gratings. The energy, as we just discussed, is measured from a temperature spike in the detector. You can get even higher resolution by creating something called a transition edge sensor, which Athena will have, where you basically keep the detector material just at the edge of superconductivity. So when a photon is absorbed, the resistance spikes, and you can measure the energy more accurately than with PRISM. But in any case, the principle of the calorimeter is that you have constant energy resolution, which means that you have higher resolution at high energy. So really, in order to have high resolution spectroscopy across the X-ray band, what you want is a combination of gratings and microcalorimeters. But crucially, the microcalorimeter, since it's non-dispersive, it means that you can actually build an IFU, and that is what PRISM is, and that is what Athena will be. And this is great for low surface brightness emission, for obvious reasons. So these are simulations of the same simulated source. It's not a real source, but I just put in a thermal collisionally ionized plasma model and pretended to observe it with these three different instruments: the Chandra ASIS instrument, the CCD, the XMM grating, and then XRISM. And what you can see is both the effect of resolution and also the different collecting areas of the different telescopes. So the blue line is Chandra, and you can see that at low resolution, at the CCD resolution, all of these lines just get smeared into a bump. And this bump is what we use in most of the time to measure things like temperatures and densities. So you can see that it will be much more powerful to have higher resolution. And what you can also see from the black line, which is the RGS, is that over this bandpass, you can actually see the resolution get better as you go to lower energies. And down at oxygen 7, it's very clear. I mean, this is the exact same spectrum, so it's very clear that the instrumental profile of resolve is worse than, or is wider than RGS down at oxygen 7. But up at neon 9, it's not quite so bad. And if you were to go up to, say, 2 keV, then XRISM would start to win. So if we look at a higher temperature plasma, so this is now a 4 keV plasma, about 46 million degrees, observed with the gratings. Now we can't use XMM RGS because it only goes up to about 2 keV. So I have instead simulated the Chandra high energy transmission grating. The iron 25 complex that you see here is now not really very well resolved by the Chandra grating, and instead you really win by going to the microcalorimeter with XRISM. That was a simulated data set. This is the real thing. This is the spectrum of the Hitomi, of the Perseus cluster with Hitomi. And what you can see is that they were able to measure the Doppler broadening and measure the turbulent velocity within the Perseus cluster because it's wider than the Hitomi response, which is shown there in purple. So this is what 5 eV resolution looks like up near the iron K alpha lines. So I guess it's worth reviewing, just for the people who are not familiar with this history, how we got here and why it is that, like, we talk about Hitomi and now we're talking about XRISM. So a long time ago, there was this idea to put a calorimeter in space, an X-ray calorimeter, and one of the first serious considerations of that was for Chandra. Back when it was called AXAF, there was sort of two components to that, the imaging and the spectroscopy. They separated them out, and ultimately only the imaging one flew, and that's what we know as Chandra. So the spectroscopy capability was then picked up by Japan, and in around 2000 they launched Astro-E, but as you can see from this image on the left, it failed to reach orbit. So Astro-E failed, but they tried again several years later with Astro-E2, which was called Suzaku. Suzaku did manage to reach orbit, and that was just fine, but the calorimeter needed helium cryocooling, and unfortunately, shortly after launch, the coolant all vented, and so they were no longer able to use the microcalorimeter on board Suzaku, and instead it became a very productive imaging instrument. But you know, we were still waiting to get the microcalorimeter data. So the next attempt was Astro-H, or Hitomi, and for Hitomi they actually added to the back a hard X-ray imager, which is that boom that you can see extending out the back. And the reason that you'd want to do that is because when observing things like AGN, it's really nice to have both the soft and the hard component observed simultaneously. So Hitomi had a similar but better spectrograph than was on Suzaku, and it performed beautifully. And so that's where we got that wonderful Perseus data from, as well as shorter observations of a couple other astronomical objects. Unfortunately, there was a mishap, as you probably know, and Hitomi more or less spun itself out of control, and the solar panel snapped off, and the boom snapped off, and the mission was lost. So XRISM is the next attempt, and I think this tells you that this is hard to do, but we're very optimistic that XRISM is going to launch and not have problems and perform well, and the launch is expected around 2022 or 2023. All right, so this is going to be sort of a little detour because this is a tutorial into the methods of X-ray astronomy. There's obviously a lot of them, so I'm just going to very briefly go over how we do this for hot gas. The quantities that we would like to know are the mass, the temperature, the metallicity, the velocity, maybe a couple others that you can think of. So for a collisionally ionized plasma, what we call a thermal plasma, and this is just using the APEC model from AtomDB, the temperature can be measured by the different ions that are present, or the lines from the different ions that are present. So this equation at the bottom, where the flux is proportional to what's called the emissivity times the emission measure. The emission measure is the amount of stuff, and so that's how we can measure the density if we can constrain that. But to do that, we also have to constrain this emissivity, which is a function of both the temperature and the metallicity. So from the temperature we get from, for example, if you look at the top right, you can see the oxygen ion fraction is a function of temperature. So if you see that you have more oxygen 7 than oxygen 8, the blue shaded region is sort of the X-ray band, then you would know that you have a cooler plasma. So you can do this type of thing for a number of different species, and by comparing the strengths of the different lines, you are able to constrain the temperature, which we do by fitting what we call a global fitting over the whole bandpass and seeing what ions are present. And then from the ratio of the metallicity, or ratio of the lines to the continuum, we can measure the elemental abundances. In practice, this doesn't look all that pretty, especially at CCD resolution. This is what are called folded spectra. So these are this is the two XMM instruments looking at the exact same thing. And the reason they look different is because the effective area, the collecting area as a function of energy is different for the two instruments, and the spectral resolution is also a little different. And you might ask, well, why can't we just unfold this? You know, why can't we take this and go back to something that looks like this? And the reason is that when an X-ray is absorbed, it has a chance of being detected at the energy that it actually has or at any lower energy. And that's because as it's absorbed, some of the energy can be lost. Some of it can like scatter out as an electron into a neighboring pixel or something like that. And because of that, it's actually very hard to invert the spectrum to get back to what we know is the truth. So what instead we do is what's called forward fitting, where we, and we've heard about this already in this meeting. So we generate a test model, simulate an observation using that, the telescope model, and then compare to the observed data. Another thing that you'll probably hear a lot about is these helium-like ions, and these can be used to diagnose the density and temperature within a certain regime without having to fit the whole spectrum. And that has to do with just the properties of this so-called triplet of lines, the resonance, intercombination, and forbidden lines. So for example, the forbidden transition, it takes longer to decay, so it can be suppressed if electrons that are sitting at that level are being collisionally depopulated because you have high density. And charge exchange can also result in a high forbidden to resonance ratio. So if you are interested in getting involved in X-ray astronomy with XRISM, it would be worth learning about the helium-like triplets. For velocity, in terms of direct measurements, I think that right now, for bulk flows at least, pretty much all we can do is use Doppler shifts and resonance absorption lines. And the Milky Way is currently the only place where we can really directly measure the kinematics, and indirect measurements are possible in a few galaxies. But this is something where XRISM and ARCIS will really help. So this is an RGS spectrum, XMM RGS spectrum of Markarian 421, which is an extremely bright blazar. And what you can see is that referenced in the inset is that referenced to the laboratory wavelength, which we calibrate from this bright star Capella, there's a Doppler shift. So you can do that for different lines across the sky. But with XRISM, we'll be able to do much better. So XRISM is really good for clusters. I think that you know, you've probably heard about all of the stuff that microcalorimeters can do for clusters much more than anything else, because that's some of the most spectacular work. So these are simulations done by Aurora, who contributed this to the XRISM science white paper, which you can find on the archive. And XRISM is going to be able to measure like the dynamics of cluster mergers, measure precise masses for using clusters in cosmology, and determine how AGN feedback heats the ICM and mixes the metals into it. So if you're interested in clusters, and I know that many of you are, XRISM is going to be absolutely fantastic for that. The question, though, is that I wanted to get at is how does it do for L-star CGM science? And since Jess had encouraged us to use emojis, I tried to do this. And I think what you can see is, like, on the left, the instruments that we have, Chandra and XMM and now eRosita, are really not very good for L-star CGM science. They're good for some things, especially at higher halo masses, but for Milky Way sized galaxies, other than perhaps the Milky Way itself, they're really not all that spectacular. ARCIS, this is not really an advertisement for ARCIS, but ARCIS is designed to look at the CGM. And so, of course, over on the right, you can see that it would be just fantastic for CGM science. XRISM was not built to look at the CGM of L-star galaxies. So there are some things that it will do. There are things where it will make breakthroughs. But as I said, it's going to generally be closer to the galaxy. But I think that there's one thing in particular that you should be very excited about with XRISM for smaller galaxies is understanding outflows and the role of hot gas in these outflows. So with the remaining time, I just wanted to go briefly through three sort of case studies that are at least adjacent to the type of science that we've been talking about at this meeting. So these would be galactic wind, the temperature structure of the hot ISM, and resonance scattering. So the plot on the left is very familiar to all of you. We've seen something like this at pretty much every talk in this conference. But But the point is that stellar feedback is thought to be a driver of galaxy evolution, and it's likely, on balance, more important than AGNs in terms of number of galaxies, and it's a way to enrich the IGM at high redshift. But we still don't know what the driving mechanism for the winds are. Like we had in the outflows week, we heard a lot about galactic winds, and then in the non-thermal week, we heard a lot about cosmic rays. And I think that we still don't really have a clear answer for the role of hot gas. Is it mostly along for the ride, or is it really the driver? And how much mass is taken out? What does mass loading even mean? Right? We had a tutorial about that early on. So our goal is to measure the mass, energy, and metal content of the hot component and determine really how important it is. So one of the best places to do this is M82, which is shown here on the right, the prototypical starburst. And so this is what the data look like in Chandra. So this is, the green is the resolved field of view overlaid onto M82. The left image is showing the soft emission, and then the right panel shows a very narrow band highlighting that there is diffuse iron-25 emission as well in the center. And there's also some bright point sources, but the diffuse iron-25 is about 40% of the total emission in that band, which means we stand a chance of seeing it. So, you know, if we were to measure the velocity in the soft band, then you know, we can use some of these lines to measure the velocity in the overall nebula, and XRISM is going to do a very good job at that. So we're going to be able to constrain velocities, line of sight velocities, and velocity widths in this nebula, but we're also going to be able to do it in the very nucleus. And this is really exciting because this is the hot gas, the very hot gas that we think actually drives the wind. So if we're able to measure a very high velocity in the nucleus from the iron-25 or iron-26, then we will know that there's a lot of kinetic energy there, and then probably is an important driver. The next case study, and probably the last that I'll get to before the breakout room, is the temperature structure of the hot ISM. And I think the reason this is important, even though this is not CGM, is that currently with CCD resolution, we can pretty much only measure 1 or 2 temperature models. And as I'll show, that's very much not adequate. And so what we want to do is use the lines from multiple species to construct a temperature distribution, much like has been done in stellar coronae. So this plot here just shows the results for measured temperatures for 2 temperature best fit models as a function of the virial temperature for that halo mass. And you can see that pretty much like all halos have the same temperatures. And in fact, this is generally true that you can take the same temperature model and fit it to most galaxies in the Chandra archive. And these temperatures really don't mean anything, or at least they're not very reliable. They're loci for emission measure distributions with different shapes when viewed at low resolution. And this leads to systematic uncertainties in the pressure of up to like 500%. So there are external constraints that may reduce that, but we'd really like to know the true temperature structure. I'm just going to skip past the resonance scattering to let you know about this important result, which is that we now have the guaranteed time targets announced. So if you go to this website, which I'll post in the Slack later, you can see the targets which have been selected. Priority A will be observed, priority C may be observed, and there's actually an opportunity for you to get involved. There's going to be a call for proposals to join target teams for A priority targets. So each target is going to, it doesn't have it now, but it will list the proposed science as well as the possible needs that team has. So you will propose to individual targets, and then selection will be made by anonymous peer review, and then the guest scientists would be assigned to the target teams in advance of launch, and you'd basically get money to cover salary, travel, and publication charges. But this is a good way to get involved with XRISM early on. We're not only looking for X-ray astronomers, there is definitely room for theorists and multi-wavelength observers to join the team. So with that, I'm just going to leave this up. I talked about what XRISM could do for CGM adjacent science, but XRISM is an observatory. Many of you are interested in many different things. XRISM is good for a whole bunch of stuff. So I look forward to talking more about that in the breakout room.
Thank you, Edmund. That was amazing. I am very excited for this. So I have just opened up the breakout rooms, and it should be pretty obvious which one is which. The you say XRISM, right?
You call it XRISM.
XRISM? Okay, XRISM. Huh.
It will be renamed on launch, so you know, don't get too attached to the name.
All right, well, there's a XRISM room, and that's the room you go to if you want to talk more about XRISM. And let's take a 2-minute break, and at exactly 8:40 a.m., I'm going to ask Dylan to begin. So Edmund, if you can head over to your breakout room, and Dylan, if you want to start sharing your slides, if you have them, you are welcome to do so, and we'll start in exactly 1 minute from now.